Okay, so now thermonuclear supernovae. I changed my title slide, especially for Chris, but Chris has left, I think, now, because he was actually always starting off with showing his title slide, saying Kokolab supernova in it, and showing a picture of supernova 1994D there, which is a type 1a supernova. So that's why I put in a simulation of a Kokolab supernova here. This is Thomas Janke's group. Okay, but we will be talking about thermonuclear supernova explosions, not gravitational collapse. Okay, so this is where we stand with our plan of the lectures. So we've discussed all the basics of what you need to understand the modeling of thermonuclear supernova explosions of white dwarfs. We talked about simulation techniques, and we also talked about progenitors and the ignition process. So now we are at a stage where we can actually take a look at the actual explosion simulations, and that's the topic for today. So I will today say some words about the goals and approaches that are taken for simulations, and then I will actually structure the discussion according to different explosion scenarios. And I will first discuss Chandrasekhar mass explosion models, deflagrations in Chandrasekhar mass, white dwarfs, and delayed detonations in these objects, and then switch to sub-Chandrasekhar mass explosions, where we'll take a look at the double detonation scenario and the violent mergers, and just say few words about other scenarios in the end. Now, doing numerical simulations of thermonuclear supernovae, of course, as always, you have to deal with a number of challenges. Numerical simulations, of course, describe a physical process but have parameters in it, and the parameters could be in principle grouped into several categories. So the first category would be the physical parameters of the model. So this is actually what characterizes your setup. So this could be, for instance, the central density of the white dwarf at explosion, or its chemical composition. So this is something that you actually would expect to change in nature from object to object as a physical parameter. Then we have modeling parameters, and these are due to uncertainties in the theoretical description. We have approximations, simplifications, and made compromises to allow for numerical implementation, and this led to certain parameters. And finally, we also have just purely numerical parameters that are due to the discretization strategy, due to limited resolution, and so on. And one has to distinguish these, and of course, the art of performing these simulations is to keep all these parameters under control, because what you want to test in the end is only the physical parameters, and you want to get results that don't depend much on the modeling parameters or on the numerical parameters. Okay, so this applies to all simulations, numerical simulations of astrophysical objects, and of course to thermonuclear supernovae as well. These are rather complex objects to simulate, involve multiple physical mechanisms in a wide range of scales in length and in time, as we discussed already. So therefore, we have to make compromises here. So I will review some recent simulations, as said before, that address different explosion scenarios. I will focus here on recent multidimensional simulations that attempt to capture the physical processes in a consistent way, because our goal here is to discuss the physical principles. But before doing so, I will give some credit for 1D simulations as well. So these have been performed by a number of authors over a number of groups over several decades now, and they of course also have their value. They provide very nice fits to observables, and they can also be used to test for specific effects in the explosion mechanism in an efficient way, because the computational demand of these one-dimensional simulations is significantly lower, so you can explore the parameter space much better. You can tune these very finely to fit observations. So all this is of course an advantage, but the major drawback is that they involve very strong tunable parameters, model parameters, because of the inconsistent representation of the physical mechanism. So therefore it is actually then difficult to draw firm conclusions on the explosion physics from such simulations. Now, the initial conditions for type 1a supernovae explosions, for thermonuclear explosions, as we discussed, are uncertain, it is likely that the parameters of the exploding white dwarfs prior to ignition vary from object to object, and the question is, does this give rise to the observed diversity of type 1a super? So that, of course, depends on the mechanism you study, and each of these mechanisms has its own physical parameters, and with numerical simulations you try to vary these and see whether you actually get something that looks like the observational trend. So therefore the goals are, first of all, we would like looking into a specific scenario with numerical simulations to determine whether this model produces a viable explosion at all. And then the second order question is, does it actually reproduce single observations of type 1a supernovae, or at least some gross features of type 1a supernovae? And then the final question is, do the physical parameters of the model lead to a variability that matches the observed spread of characteristic properties of a certain subclass of supernovae or supernovae as a whole group? Okay, so first scenario I want to discuss is Chandrasekhar mass explosions. The evolution towards of a white dwarf towards the Chandrasekhar mass is uncertain. The parameters, however, that are expected to vary from object to object in nature are the white dwarf structure at ignition. So in particular, its central density could vary from object to object. Its chemical composition, metallicity, for instance, could be different in different objects, or also the carbon-oxygen ratio, and rotation is another parameter. So these are the physical parameters of the Chandrasekhar mass explosion model. The model parameter is the unknown ignition geometry, so I discussed this yesterday. This cannot be captured by explosion simulations themselves. It has to be tested offline with specialized approaches. So I've shown you some movies of Mike Zengali and his collaborators, but still the results are hard to interpret and maybe also don't reflect the real physical conditions at white dwarf ignition, although they give a good insight. So therefore, in the actual explosion simulations, what one currently does is that one ignites the flame artificially. Of course, in a complete picture, you would think that by physics of the progenitor evolution and the ignition, all this should be fixed according to the properties of the progenitor. So the point where the ignition takes place and the conditions under which the ignition takes place should be fixed by the turbulence condition and by the properties of the white dwarf, its density and its chemical composition. So the fact that the flame ignition is artificial in the model is due to our incomplete understanding of the involved ignition physics. So this is a modeling parameter. Okay, so Chandrasekhar mass explosion. So we take a carbon-oxygen white dwarf at Chandrasekhar mass and ignite it artificially, because we don't know in detail how this happens in nature. So how do we ignite it? Well, can we ignite it as a detonation? Well, this doesn't work for two reasons. For the first reason you could give is we discussed the pre-ignition convection yesterday. So the ignition of burning happens in a highly convective environment, in a very turbulent environment. So it's hard to believe that there will be sufficient thermal preconditioning in order for a detonation to trigger by the Zeldovich gradient mechanism. For instance, you would have to have a very smooth and shallow temperature gradient, and it's hard to see how this could work in such an environment. The second stronger argument, however, is due to the structure of white dwarfs of Chandrasekhar mass at hydrostatic equilibrium. We know from spectra observations of spectra of type 1a supernova and from the gamma rays that a type 1a supernova should produce about half a solar mass of nickel-56 and substantial amounts of intermediate mass elements, silicon, sulfur, and calcium, and so on. Now, near the Chandrasekhar mass, a white dwarf in hydrostatic equilibrium has a fixed structure which is virtually independent of temperature and only weakly dependent on the chemical composition. So this uniquely fixes the density profile of the white dwarf or a Chandrasekhar mass, and what one gets is a very compact structure, and this is illustrated here on the right-hand side plot made by Ivo Zainzar and Dean Townsley. Here what you see is the density of the material as a function of the enclosed mass inside the white dwarf, and the green line here, that's a Chandrasekhar mass white dwarf at hydrostatic equilibrium, and you see that the largest fraction of the mass of this Chandrasekhar mass white dwarf configuration at hydrostatic equilibrium is above density of 10 to the 7 grams per cubed centimeter. So we have almost all the mass above 10 to the 7 grams per cc. And above that density, a detonation will turn the material into iron group elements into nickel and stable iron. So that means if we ignite a detonation in a Chandrasekhar mass white dwarf at hydrostatic equilibrium, it will burn the entire white dwarf, or almost the entire white dwarf, to iron. And this is inconsistent with the observations. The reason for this is that a detonation is supersonic, so there is no pre-expansion of the material. So once you ignite the detonation in the center, it will propagate outwards supersonically, and the star, the material ahead of the detonation will not know that any energy release happens behind it, because there's no causal contact, because the detonation is supersonic. So the material ahead of the flame does not pre-expand. So you burn the entire white dwarf at this hydrostatic equilibrium configuration, and that means you have all the material above 10 to the 7 grams per cubed centimeters and produce only iron group elements. Now this is inconsistent with the observations, because you need to make intermediate mass elements, silicon, sulfur, and calcium, and so on. So that means that burning has to take place in large parts of the material at low density. So that implies that the fuel in a Chandrasekhar mass white dwarf explosion cannot remain in its hydrostatic equilibrium stratification when it's incinerated. So that means we need substantial pre-expansion prior to burning. And this is only possible if the combustion wave starts out subsonically as a deflagration, because then you have causal contact above the combustion wave. The energy release behind the deflagration actually make the star expand, and then of course the deflagration will see part of the material at lower expanded densities. So how does that work? Well, the deflagration ignites near the center of the white dwarf star, and this also implies that we have instabilities and turbulence. So in the end, when we start out our picture with a deflagration in a Chandrasekhar mass white dwarf, then we will have turbulent deflagrations. The reason is the flame starts out in the center of the star, so this is a wedge in the star. The reason the flame starts out in the center and propagates outwards. It leaves behind light and hot ashes, in which due to the high temperature, the degeneracy is partially lifted. So therefore, we have, when you assume here's the flame front and here's the ash material, here's the fuel material, you have a density jump above this, and the fuel density ahead of the flame is denser than the ashes behind it. Now, the gravitational field of the white dwarf star, of course, points upwards, and that means that you have an inverse density stratification in the gravitational field of the star, and this is buoyancy unstable. The Rayleigh-Taylor instability in its nonlinear state, as we discussed it yesterday, will lead to these bubbles of material, of burning material, rising into the fuel. These take on these mushroom cup shapes, and in between these rising burning bubbles, we expect downdrafts of unburned material. Now, at the interfaces of these bubbles, so this is where the flame is then located, the Kelvin-Helmholtz instability will become active, because we have strong shear flows here, and this will lead to the production of turbulent eddies. And in the end, a turbulent cascade will form, and the flame will interact with strong turbulence. One can estimate the situations, the conditions around such a Rayleigh-Taylor bubble. So let's say we have typically maybe something like a density of 10 to the 9 grams per cubed centimeters. The viscosity of white dwarf material is about 1 square centimeter per second, and a typical size of such a Rayleigh-Taylor bubble is on the order of 10 to the 7 centimeters or so. For this bubble, you can actually calculate by an analytical estimate the rise velocity, and you will find that this has typically a velocity on the order of 10 to the 7 centimeters per second. And with that, you can actually calculate the Reynolds number, given as the density times the velocity times length scale over viscosity, and that gives you a number of 10 to the 14. So you have huge Reynolds numbers, and this means that turbulence is unavoidable. So strong turbulence is naturally expected in these models. Now this is something that I always like to stress, because if I go to conferences and meet people there who do 1D simulations, they would say, well, our models fit much better if we actually have a more stratified ejecta composition. So can't you just suppress this turbulence in your models? And the answer, of course, is no, you can't do that, because in a multi-D model, turbulence can neither be avoided nor ignored. It's actually an intrinsic physical effect. So strong buoyancy and flame instabilities will lead to flame turbulence interaction. Without such a flame turbulence interaction, the propagation of the flame would be laminar, it would be very slow, and it would reach the burning threshold for density for deflagration, which is around 10 to the 7 grams per cubic centimeters. Below, you don't have deflagration burning anymore, before consuming substantial amounts of material. So in this case, no powerful supernova explosion would result. The only reason why in multi-D you get actually a powerful explosion of the star is that you have acceleration of the flame due to the interaction with turbulence. So any valid model for deflagrations in white dwarfs has to take these effects into account. Now this has been done to a certain degree also in classical 1D models. These of course assume spherical symmetry, and therefore do not allow for multidimensional instabilities and turbulence directly. So the measure that was taken then to at least take this into account in a parameterized way was that one prescribed an artificially enhanced flame speed, and this was in some cases motivated by mixing length theory. So this, I think, was the idea behind the W7 model of Kanemoto, and some people also talked about models that were inspired by fractal geometry of a turbulent flame. Now the outcome of these simulations is in any case sensitive to the assumption you make on the flame speed. So the flame speed in the end is the powerful tunable parameter of these one-dimensional deflagrations in Chandrasekhar-Mars white dwarfs models. So you can set this flame speed in these 1D models as being time dependent in radial direction, and then you can construct models that actually fit the observables well, and indeed many of these models have passed a number of observational tests. So what does it mean? Well, these models are still are quite successful in reproducing the observables. So therefore, possible implications for multi-D models are that the average radial flame propagation velocity in a Chandrasekhar-Mars model should be approximately similar to the values that you find, for instance, in the W7 model, which is about a third of sound speed. And the other implication is that even with the multidimensional effects, on average, the explosion products should not be very asymmetric, and that applies to density and composition. So what is the situation we find in multi-D 3D simulations of deflagrations in Chandrasekhar-Mars white dwarfs? Well, here's an example. This is a Chandrasekhar-Mars carbon-oxygen white dwarf, and it is ignited artificially at the center, and for this model we have chosen a large number of ignition bubbles placed here in the center, and then the flame propagates outwards, and it is as expected subject to these buoyancy instabilities leading to these mushroom-shaped features of burning material that rises into the fuel. The flame propagates through large parts of the white dwarf star, and at some point about 1.5 seconds after ignition, the star is expanded so much that the flame then sees rather low fuel densities on the order of 10 to the 7 grams per cubic centimeters, and then burning ceases. We follow these simulations, however, for much longer, up to 100 seconds, to represent the freeze out of turbulent motions and to approach the phase of homologous expansion, which is then needed to connect to radiative transfer calculations. So I want to show this in a movie. So here is one of our simulations. Again, a Chandrasekhar-Mars white dwarf ignited in the center in multiple sparks. The flame propagates through that, burns through this white dwarf. due to the large-scale Rayleigh tail instabilities, and it's accelerated on small scales due to interaction with turbulence. So this is a simulation that was performed with the methods that we discussed yesterday. The flame front is described by the level set approach, so it's actually modeled as a discontinuity, and in order to take the flame turbulence interaction into account, we rely on a turbulent subgrid scale model. So this is an LAS simulation of a deflagration in a Chandrasekhar mass white dwarf. So the outcome is illustrated here. So this is from this simulation the predicted chemical structure of the ejecta. So what I've color-coded here is the composition. So bluish material is carbon oxygen. So this is predominantly seen at the surface. Then you have intermediate mass elements in green. And you see some of these features due to these Rayleigh tail instabilities that come up here and are filled with mainly intermediate mass elements. And the iron group elements I've color-coded as the red color component, and this is predominantly seen in the center. Makes, of course, the overall color then sort of white or yellow. But what you could see in the last snapshot here was that also in the center you have a rather mixed structure of the ejecta due to these large-scale instabilities. You still see some unburnt material very near the center, and also intermediate mass elements very near the center. So the typical results for such simulations of turbulent deflagrations in Chandrasekhar mass white dwarfs is that you see clear imprints of the large-scale plumes, the large-scale Rayleigh tail features. The ejecta are not really clearly stratified, so we have usually iron group elements, intermediate mass elements, and carbon oxygen material at the same radii. That does not really mean that they are microscopically mixed, but if you actually do an average over angles, then you will actually see that you have co-spatial regions that are filled with these groups of elements. An example model that's sort of typical would produce something like a kinetic energy of 8 times to the 50 8 times 10 to the 50 ergs. Nuclear synthesis post-processing, as we discussed it yesterday, was done for this model with 53 cube tracer particles, and from that one gets a total iron group element production of 0.56 solar masses. Nickel 56, however, is only 0.33 solar masses of this, because in a deflagration we have strong neutralization due to electron captures, because the burning is slow in the beginning, so the material stays at rather high densities and can neutralize quite substantially. We have low production of intermediate mass elements, at least as compared to the predictions of one-dimensional models, and substantial amounts of unburnt material. So this actually makes these turbulent deflagrations in Chandrasekhar mass white dwarfs no good model for normal type 1a supernovae. The nickel 56 production that you can achieve here is at the lower end of the expected range, so 0.33 solar masses is not completely out of the range for normal type 1a supernovae, but it's really the lower end. And it cannot be much increased. And the ejecta are strongly mixed, so this is also nothing you would actually expect if you keep in mind that 1D models produce better agreement with the observations when they are more stratified. Nonetheless, the parameters of these models were tested, and we tested first of all the model parameter, that is the ignition geometry, because this has the strongest impact on the outcome. Multi-spot ignition, as we discussed yesterday, is not supported by current pre-ignition convection simulations. It is, however, a strong numerical parameter, a strong modeling parameter, and you can use it to determine how much variation in brightness and energy release is possible in a turbulent deflagration in a Chandrasekhar mass white dwarf. It can also be seen as a way, this multi-spot ignition, of inducing seeds for the Rayleigh tail instability in a controlled way, because if you just put in one bubble of center, it's very hard to set up something that is really a suitable numerical setup for convergence studies, because then the seeds for the Rayleigh tail instability will be just set by the resolution by discretization errors. So therefore, starting out with something that excites different modes of the Rayleigh tail instability seems to be a better controlled way of doing it. So here is the setups for a sequence of studies that were done by my former postdoc Michael Fink. So he ignited the center of the white dwarf as a deflagration in varying numbers of ignition sparks at varying locations. So here you see the models that he has tested. So he ignited in some cases in very sparse ignition scenarios, and in other cases he put many ignition sparks near the center. The sparsely ignited models lead to an asymmetric propagation of the flame, because if you put in only 2 or 3 sparks, then this will be asymmetric. And this actually produces rather little energy, the typical evolution you see here. So you ignite the flame maybe into spark here, and then this buoyantly rising plume will go up to one side of the star and break out of the star. But the energy release here, due to the very incomplete burning, is low, and it is insufficient to completely unbind the star. So what this actually will leave behind is a bound remnant in the center. If you ignite in many sparks, then you can actually achieve a rather complete burning, where the center is also burned and the white dwarf is completely disrupted. Now this is summarized here. The results where the ejected mass is plotted against the nuclear energy release in the different models, and the numbers here refer to the numbers of ignition sparks. And you see that only if you have a high number of ignition sparks, say above something like 100 or so, then you actually completely unbind the star, and the ejected mass is 1.4 solar masses, the Chandrasekhar mass. And below that, you actually eject only part of the total mass. The other important number given in this plot is the nickel 56 mass. That's actually given here by these red dots. And you see that there's not much variation. So the nickel 56 masses that we find in these models range between 0.03 solar masses up to, at best, 0.4 solar masses. So that means no matter how vigorously you ignite these models, it is hard to actually reach nickel 56 masses that are above something like 0.4 solar masses. And this is too faint to produce the range of normal type 1a supernovae. However, this model, as I will discuss tomorrow, actually may be a good explanation for a certain subclass of type 1a supernovae. Now, the physical parameters of the models, of course, are the central density at ignition, the chemical composition at ignition, carbon-oxygen ratio was shown to not have a strong effect on the outcome, metallicity effect due to neon-22. This is something we discussed yesterday. This is seen in these models, and I also showed a plot of post-processing taking this neon-22 effect into account by Claudia Tavares yesterday. Rotation does have a strong effect, and this was tested by Jan Fannes a while ago. So the effect here is that by rotation you can increase the mass of the white dwarf. But the problem is, if you have strong rotation, then the Rayleigh-Taylor instability will be suppressed in the angular plane because of angular momentum conservation. You cannot easily shuffle material in the radial direction around, because this will violate angular momentum conservation. So that means that the deflagration will produce instabilities and buoyantly rising bubbles predominantly along the rotation axis, but not perpendicular to it. And therefore, the effect of turbulent instabilities is not very strong and is suppressed by rotation. Okay, so uncertainties and conclusions. Well, the modeling of the flame turbulence interaction still has uncertainties. Yesterday I talked about how this is done in detail with buoyancy scaling or with turbulent subgrid scale models. And of course you could say, well, this is still an uncertain subject. But I would say that current approaches have already reached a rather high level of sophistication. We have performed tests of the turbulent scaling properties in such large-scale simulations, and they showed consistency with the modeling assumptions. So therefore, I would not actually expect much change or improvement over the next years with improving the description of turbulence flame interaction in these models. The ignition, however, remains the strongest and most uncertain parameter. the link between the pre-ignition convection and the explosion itself has not been established yet. This was actually one of the goals of the Stony Brook group. They actually designed these two codes that they have available now, the Maestro code, a low Mach number anelastic code, and the Castor code, a compressible hydrodynamics code, especially for this reason, to follow the pre-ignition convection through ignition to explosion, but this has not been studied in very much detail yet. But this is something that you could perhaps expect for the future. Okay, that's turbulent deflagrations in Chandrasekhar-Mars white dwarfs. And these produce insufficient amounts of nickel-56 to explain normal type 1a supernovae. So how can we make these explosions brighter? So if we want to have Chandrasekhar-Mars white dwarf explosions explaining normal type 1a supernovae, we have to somehow enhance burning. And this is possible if we assume an additional detonation phase after initial deflagration. The reason for this is that the initial deflagration will pre-expand the star, and then you have low densities. You don't have the star in hydrostatic equilibrium anymore, and that means that you can now allow for a detonation to burn out the rest at low densities, and it will actually produce intermediate mass elements. This is also shown here in this diagram by Ivo and Dean. The typical structure of a Chandrasekhar-Mars white dwarf at the onset of a detonation after a pre-ignition, after previous deflagration phase is shown here in blue. And you see that the density is significantly lower, the white dwarf has expanded substantially, and then actually a detonation would produce intermediate mass elements and not only iron group elements. So that's the basic idea behind delayed detonation was you pre-expand the star in a deflagration phase, and then you can have a detonation that burns out the rest very efficiently. Okay, now the detonation can produce additional nickel-56 even at lower fuel densities than a deflagration, because the detonation compresses material, so it still burns two iron group elements at rather low fuel densities at 10 to the 7 grams per cubic centimeters, and it leads to a more complete burning of the white dwarf star, because it quickly supersonically propagates through all the remaining fuel and converts it. So in the end, you produce much more intermediate mass elements and very little unburned material. So this looks promising for explaining normal type 1a supernovae. An effect that I want to point out here is that, of course, the efficiency of the detonation is set by how strong the deflagration before was in order to expand the star. And in order to illustrate this, I have these two simulations here. So we have the same Chandrasekhar-Mars white dwarf ignited in different ignition scenarios for the deflagration. Here we have a weak ignition and only few sparks. Here we have a strong ignition and many sparks. So here we have a strong deflagration. Here we have a weak deflagration, as you see here. So now when the detonation triggers, I'll jump forward. When the detonation triggers, so this is this front here, this shows the detonation, we have for the weak deflagration and only very weakly expanded white dwarf. For the strong deflagration, the star has expanded quite a bit. So that means that the detonation will see the material at rather different densities. So for the weak deflagration, we have a very strong detonation in the end, because the star has not expanded so much, and the detonation sees material at high densities and burns out the center of the star to iron group elements that are shown here in red. Whereas for a strong deflagration, the star has expanded in the deflagration phase already quite substantially, and then the detonation does not contribute as much to the overall burning. Now, these delayed detonations were also tried to be addressed with one-dimensional simulations. The mechanisms for triggering delayed detonations, however, all rely on multidimensional hydrodynamical effects. So therefore, they involve asymmetric flame propagation, and all this cannot be captured realistically in one-dimensional models. One-dimensional models nonetheless have been simulated, so they usually run a deflagration in 1D and at some point just assume a transition to a detonation at a certain prescribed transition density as a parameter, and then follow the detonation. So that means this introduces an additional free parameter that can also be used to tune the models, and actually this then of course gives also rise to other good matches with the observations. One has to notice, however, that In this model, the deflagration in 1D burns outwards to a certain radius, that it transitions to a detonation, and detonation burns further. But that means that a detonation only works in the outer layers and cannot propagate backwards, which is very different from multi-D models, because in multi-D models, the detonation can actually burn down the unburnt material that's left behind near the center by these downdrafts in these large-scale radially Taylor unstable bubbles. Now the fundamental question for the delayed detonation scenario is how you actually trigger the detonation after a deflagration burning phase. And one possibility is by so-called deflagration to detonation transition. So what one means by this is a spontaneous transition of the combustion wave from a deflagration mode into a detonation. So this is actually an effect that is observed for technical combustion, but in these cases it's always associated to boundary effects. So usually this happens at the boundary of a combustion vessel or at obstacles inside the combustion volume. So if car engines knock, this is deflagration to detonation transitions, and this is avoided by a high octane number of the fuel. But in the astrophysical situation, we want to have a deflagration to detonation transition that works without boundaries, because we don't have boundaries in the supernova in the star. So therefore what we need is an unconfined deflagration to detonation transition. Whether or not this is possible is unclear also in the terrestrial combustion community. One possibility is that since we have strong turbulence, maybe these turbulent eddies can break up at some point the flame and precondition the fuel material with shallow enough temperature gradients to allow for a detonation ignition by the Zeldovich gradient mechanism or by the Swayze mechanism that I explained yesterday. Now this is just a possibility that was studied as much as possible, but still the conclusions are not very firm. However, it is clear that if such a spontaneous deflagration to detonation transition was to occur, then it needs to happen at rather low fuel densities, below 10 to the 7 grams per cubic centimeters. So that means at a late stage in the deflagration burning. And this is because then the flame width has become very broad, and the Gibson scale is low, and the flame interacts, the internal flame structure interacts with turbulence, and this can modify the internal flame structure so that a shallow temperature gradient can be achieved there, so that the gradient mechanism can ramp up a detonation. In detail, however, this has not been proven, and it's hard to identify these microscopic hotspots that, due to turbulence, achieve conditions for detonations in a large-scale Type 1a supernova simulation. So here I have shown in the background the turbulent flame structure, and I've color-coded here in red spots where high turbulence exists at still favorable densities. So these may be actually spots where a deflagration to detonation transition can happen, but of course these transitions cannot be resolved at a microscopic level. So therefore one usually uses an artificial prescription, identifying the locations for suitable conditions for deflagration to detonation transitions. Then of course depends also on the resolution you have in the model, because if you have low resolution you will actually not find so many hotspots with high enough turbulence. So therefore the best way to do this is actually to base all this description of a deflagration to detonation transition on a subgrid scale model that makes it resolution independent and allows for convergence of the models. And this was actually then done, constructed by a former PhD student of mine. Now if such a transition happens, the situation evolves as here. We have the white dwarf star, the density is color-coded here in the equatorial plane. The blue isosurface is the deflagration flame, and the detonation then happens at some point of this deflagration flame, where at low densities high turbulence is still there, so that a DDT can perhaps happen. And then out of this point a supersonic detonation wave will propagate, and it will burn through the remaining parts of the fuel and engulf the complicated instability-driven deflagration structure, as you see here. So this is what is shown in the movie of such a typical simulation here. Again, this is a Chandrasekhar mass, carbon oxygen white dwarf, ignited in the center in a number of ignition sparks. Here we see the deflagration to develop. Again, in this model, the deflagration is described with the level set method as a sharp discontinuity, and its interaction with turbulence is modeled with a turbulent, a subgrid scale turbulence model. Now, deflagration propagates through the white dwarf star. The rotation here is artificial. We just actually made this thing rotate in order to show all the different sides and viewing angles of the star, but this is a non-rotating model. And at some point, the conditions that we think are necessary for triggering a detonation are met. This should be happening soon here, and then the detonation starts to propagate through the remaining part of the fuel. It also burns down into the central regions where these downdrafts in between the radiator bubbles have left behind unburned material. Okay, now this scenario has also been tested for model parameters. Again, as I said before, the deflagration strength determines the efficiency of the detonation. Sparse ignition leads to strong detonations in the end because the star does not pre-expand so much, and therefore more nickel-56 is produced and we get bright events. So this seems to be rather easy to achieve in this model. Bright events are easy, but the question is how faint can such a deflagration detonation model be? Because in the end, in order to make it faint, you have to pre-expand it as strongly as possible with the deflagration. So the strongest deflagration that you can get determines the faintest DDT model. And this was tested in, again, a number of simulations varying the ignition spark geometry, similar to, or it's exactly the same setups that we also used for studying the pure deflagrations, but now we actually added a detonation phase in these models. And what you get is summarized in this plot. So this is the mass fraction of total mass plotted against ignition kernels in the deflagration phase for different models. And what you see here is that the more ignition kernels you have in the deflagration, the stronger is the deflagration and the weaker is the detonation, and therefore the overall production of nickel-56, that's shown here in red, decreases. So you get nickel-56 masses in between 0.3 and 0.8 solar masses. So this is consistent with the expected range of brightnesses of normal type 1a supernovae. And I particularly want to highlight this model ignited in 100 sparks here because this is at the moment our standard model for producing normal type 1a supernovae. So this here actually produces about half a solar mass of nickel-56. The problem, however, is that the fainter events with 0.3 solar masses of nickel-56 that should be actually within the range of normal type 1a supernovae can be achieved only with very extremely strong deflagration. So here we have to assume an ignition in something like 1600 sparks or so, which seems unlikely from the current results of pre-ignition convection simulations. What are the physical parameters of the model? So this was a modeling parameter, and the physical parameters are the central density at ignition. Here controversial results have been published in literature. The differences, however, are attributed to differences in the implementation of the deflagration to detonation transition. The chemical composition at ignition was also tested. So a student of mine, Sebastian Ullmann, tested the carbon-oxygen ratio. Of course, if you have a lower carbon-oxygen ratio than burning to nickel-56, you will release less energy. So therefore, you can actually, with this ratio, moderate the overall energy release in the explosion. But the effects are small compared to the very powerful parameter of the ignition of the deflagration. Rotation was also tested again, and it's again a strong effect by the same mechanism that I described before. We suppress the growth of the radial instability in the equatorial plane. So this is actually shown here. So this is a differentially rotating white dwarf star with about 2 solar masses. You see that its shape is heavily deformed. It's sort of a donut shape already. And we ignite it in the center, and then the deflagration propagates predominantly towards the poles because the radial instability is suppressed perpendicular to the rotation axis. And this is then also where the detonation happens. The outcome here is that because of the very weak deflagration by suppression due to rotation, the star doesn't pre-expand a lot. You have anyway 2 solar masses of material, and you produce a huge amount of nickel-56. So these will be very, very bright events if they were ever observed. Okay, so there are other variants of delayed detonations in Chandrasekhar mass white dwarfs that don't rely on a spontaneous transition of the flame from deflagration to detonation in a deflagration-detonation transition, but on other mechanisms. So one of these is the gravitationally confined detonation scenario that was proposed by the Chicago group. So the idea here is that one starts out with a deflagration that is ignited off-center in a single spark or a few sparks off-center, so that one gets an asymmetric flame propagation and an inefficient burning in the deflagration phase. Then the flame breaks out of the surface of the still bound remnant, and it is gravitationally bound and therefore slides around the bound remnant and collides on the antipode of the breakout point. And this collision is claimed then to trigger a detonation. So the movie here by the Chicago group illustrates the effect. So this is again a Chandrasekhar mass white dwarf, and here the ignition is in one single bubble off center, and you see the Rayleigh-Taylor instability driving it outwards, the buoyancy instability. The burning is not very strong, so the star stays bound. The material slides around the star and clashes on the other side, and here a hotspot then is formed in the collimation of the deflagration material, and this is supposed to trigger then a detonation by compression. So that's the effect here. So this is the idea of the gravitationally confined detonation scenario. There are some challenges to this model. So first of all, it's not clear how robust the detonation triggering is. So we've looked into the possibility of achieving high enough temperatures and densities in the collision region to trigger a detonation. And the outcome is that this actually works only if you have very inefficient deflagration burning, so you need actually to have rather little pre-expansion of the star in order to have still high densities and achieve high temperatures in the collision region. If you have strong expansion, of course, then this deflagration material may still slide around the surface of the star and collide on the other side, but it will do so under conditions of rather low densities and therefore not trigger a detonation. So you need little pre-expansion in order to achieve conditions for triggering a detonation. It's questionable of whether with realistic deflagration ignition scenarios this is achievable. So this actually then leads to the problem of how to reach faint events. Because in order to have a faint event, you want to have quite strong expansion of the star before the detonation triggers. Otherwise, the detonation will burn everything in the core to iron group elements. But this counteracts the effect that you want to have little pre-expansion in order to be able to detonate in the first place. Another potential problem is that from the movie you've seen before, it is clear that the inner part of the ejecta will be dominated by the ashes of the detonation, but the outer part of the ejecta will be the deflagration ash that covered the surface of the star. So that means that in the ejecta you expect to have stable iron at the highest velocities, and this could be inconsistent with the observations. So we've recently tested this by radiation transfer calculations, and it seems that this actually has a strong effect on the predicted observables and drive them away from a good match with the observations. So this is unlikely to account for normal type 1a supernovae. However, there is the possibility that was suggested a while ago by Carl Jordan that this gravitationally confined detonation mechanism is assisted by pulsations, and only in the pulsation phase the detonation triggers, and then it may be even possible to achieve fainter explosions. A last variant that I want to mention here for the delayed detonation scenario is the pulsational delayed detonation. So here again one starts out from weak deflagrations that are unsuccessful in unbinding the white dwarf. This leads to pulsations that are actually observed in many simulations of various groups of the white dwarf. Now the claim is that an accretion shock in this backwards, the contraction phase of the pulsation forms above the carbon oxygen white dwarf. This confines the core and transforms kinetic energy of the inflating material into heat and triggers a detonation. That's at least the claim there. It has not been shown in detail that this really works, but if a detonation triggers, then the claim is that 0.6 to 0.8 solar masses of nickel-56 could be produced as a model of normal type 1a supernovae. The potential problems with this scenario is whether or not detonation triggers. This has not been shown in detail. And again, as for the GCD model, you have deflagration ashes in the outer layers of the ejecta. So summary of the delayed detonation model is uncertainties and conclusions. So in principle, it could be a promising scenario with many variations in the mechanism. Some of these variants seem to be able to cover the nickel 56 and energy ranges that are required for normal type 1a supernovae, but the deflagration to detonation transition or other mechanisms of detonation initiations remain uncertain. So therefore, we have looked into subchandra mass explosions, and other groups have done so too. So this is the main alternative to explosions of chandra mass white dwarfs as type 1a supernova models. Super chandra mass protogenesis have also been suggested, but this remains a theoretical speculation, and if they explode, they would at best produce peculiar superluminous events. So therefore, for normal type 1a supernovae, the alternative candidate is a subchandra mass white dwarf. The main questions here are, do explosions of such objects produce nickel 56 masses and energies in the right ballpark of normal type 1a supernovae? This can be tested easily with toy models, as I will show. Then the question is, how is the explosion actually triggered? This is difficult to determine. And in the end, we will see that a rather vigorous dynamics is required to trigger the burning of a subchandra mass white dwarfs. And this is likely to leave imprints on the ejecta structure that could be problematic for producing observables that are consistent with the observations. Now, the general idea is that, first of all, a subchandra mass white dwarf is much less compact than a chandra mass white dwarf. So the typical structure in hydrostatic equilibrium of a 1.1 solar mass subchandra mass white dwarf is shown here as this dashed orange line. You see that you have material at rather low densities here. You reach the regime where a detonation would burn into nickel 56 above 10 to the 7 grams per cubed centimeter. So in principle, for this configuration, you could produce nickel 56. You would also produce intermediate mass elements in a detonation because the density structure is so expanded. So this, in principle, would suggest that a detonation could lead to an ejecta composition that is consistent with the observations. The deflagration is not likely to trigger here because you have too low fuel densities, and if it would trigger, it would also not propagate very far because of the low densities. So therefore, the detonation here in subchandra mass explosion model is the only viable mode of flame propagation to produce a thermonuclear supernova explosion. Another effect is that because of these typically low densities that you have, you don't actually reach the region where you have substantial neutralization of the material due to electron captures. So therefore, the ash is dominated in the central parts by nickel 56, and you don't produce a lot of stable iron group elements. Substantial amount, however, of intermediate mass elements are expected. Now this can be tested with toy models, so we have set up a sequence of such toy models a while ago. So the idea was to artificially detonate from the center subchandra mass white dwarfs of various masses. And we actually varied the mass in between 0.81 and 1.15 solar masses, and this then produces nickel 56 masses in a detonation that vary between 0.01 solar masses and 0.81 solar masses. So this is quite the range that you would expect for type 1a supernovae. In particular, if you want to achieve something that is the standard normal type 1a supernova, you would have to produce about half a solar mass of nickel 56, and this is actually the case for a detonation in a subchandra mass white dwarf that is very, very close to 1 solar masses. Okay, so right, so lack of neutralization, little stable iron group elements are produced. The central ejecta are dominated by nickel 56. So this is actually shown here in the enclosed mass, mass fraction versus enclosed mass of various models, 0.88 to 1.15 solar masses. You see that the central parts are dominated by nickel 56, shown here in red. And of course, the more massive the white dwarf is, the more nickel 56 you produce. Then you have a layer of intermediate mass elements, shown here in blue, around that, and only the very outer layers have some unburned material. So a characteristic feature of such detonations in subchandra mass white dwarf is that you have a very strict, a very clear chemical stratification of the ejecta predicted by that model. The second question that is harder to address, as said before, is how do we actually set off a detonation in such a subchannel sigma-mass white dwarf? Because this does not arise naturally in subchannel sigma-mass white dwarfs as in channel sigma-mass white dwarfs, which actually are bound to reach carbon burning at some point. Subchannel sigma-mass white dwarf have to be somehow hit with a hammer to really set off an explosion. And this hammer could be, for instance, a layer of helium that's accreted from a companion star and covers a subchannel sigma-mass carbon oxygen core. And this is then the so-called double detonation picture. So the idea is that the helium layer gains mass until its bottom reaches thermodynamic conditions due to compression and heating that are able to set off a detonation. So then the helium layer would detonate and drive a shock wave into the carbon oxygen core. And this shock wave in the carbon oxygen core could then set off a secondary carbon detonation in this core and lead to a thermonuclear supernova explosion of the subchannel sigma-mass white dwarf. Our questions are, of course, how does this helium shell ignite a detonation in the first place? How does the helium shell detonation proceed? And whether or not the helium detonation can trigger a secondary detonation in the carbon oxygen core, and what imprints on the ejecta are left behind from the helium detonation. So all this is determined with numerical simulations. This was done already in one-dimensional models that I would just mention here in order to make the contrast to multi-D models. So in a one-dimensional model, of course, because of spherical symmetry that you assume there, the triggering of the detonation in the helium shell is always in the entire shell. Asymmetric effects can only be studied in multi-dimensional simulations. And then, of course, new questions arise. If the helium shell triggers a detonation not in the entire shell at once, but only in a single point, which seems more natural, then you, of course, break the symmetry. And the question then is, do you still drive a shock wave into the core that is strong enough to trigger a secondary detonation then? And this seems to be the case, as pointed out by Michael Fink in his PhD thesis, because of a geometrical effect. You will always have a shock wave that propagates in some way or another into the core of the white dwarf. So you have a spherically converging shock wave, and spherically converging shock waves are bound to amplify in strength. So this is actually shown in Landau-Lifshitz, at least in the German edition. I think this is a part that was left out in the English edition. So therefore, what one finds here is that the detonation ignition in the core seems to be very robust. It works for asymmetric helium shell detonation triggering and also for low mass helium shells. And this is important because these double detonation scenarios have a potential problem with fitting the observables. You have first a detonation of the helium shell, and helium has a huge energy release and is likely to burn through rather heavy nuclei. And these then you have in the outer layers of the ejecta, and these actually lead to effects on the predicted observables that are inconsistent with the observations as I will discuss tomorrow. So therefore, we looked into the question of how to minimize this effect. So what is the minimum helium shell mass that can still produce a double detonation scenario? And so Michael Fink set up a sequence of models that were based on progenitor models that are connected to the AMCVN binaries. So these were models computed by Lars Bilston and Ken Chen and collaborators. And here's a sequence of snapshots from a typical simulation. So we have the carbon oxygen core and a helium shell around this. This is actually enclosed by these two dashed lines. The ignition spot, we assume the ignition to happen in only one single spot, which we place on the North Pole. And then the detonation, the helium shell detonation, is shown here as the cyan isosurface, and it propagates around the core and drives a shock wave into the core, which you can see here as this density jump. And this shock wave in the core collimates a little bit off center and sets off a secondary detonation of the carbon oxygen material in the core. Okay, so the most fundamental question, of course, of this double detonation scenario is whether or not you get a helium shell above a carbon oxygen core to detonate. The original model would suggest that this was actually achieved by compression and heating. However, before reaching this sufficiently to trigger a detonation, you would expect, again, strong convective motions, as pointed out by various authors. And then it's questionable of whether you can easily reach the conditions for a spontaneous formation of the detonation in such turbulent flow fields. So we are back to all the problems that we had in the deflagration to detonation scenario for the late detonations of Chandrasekhar mass white dwarfs. Another possibility is that the initiation of the helium shell detonations happens by instabilities in the accretion stream. So this was pointed out by James Guerchon and Enrico Ramirez-Ruiz and collaborators. Another potential question is, can the detonation propagate at all laterally in the helium shell? The problem here is that if you think of helium shell of low masses, then the detonation would slide around the core, and behind the detonation, the material would strongly pre-expand. And this should have an effect on the burning zone inside the detonation. It would perhaps make the detonations weaker. And therefore, the question is whether with low helium shell mass, it's still possible to sustain a detonation in the helium shell material. So this was also tested numerically by Dean Townsley, but he found that for the conditions we are interested in, this is likely to still be working. Okay, so another variant of subchandrasekhar mass explosions is achieved with mergers of two white dwarfs, and in particular with the so-called violent merger scenario. So the idea here is that it follows the merger of two carbon-oxygen white dwarfs, the in-spiral merger, as here. So these are two CO white dwarfs of different masses. We have a 1.1 solar mass white dwarf and an 0.9 solar mass white dwarf. And we follow the in-spiral and merger of these objects. So this is done here with smooth particle hydrodynamics. You see that by strong tidal interaction, the lighter and more extended secondary star is disrupted, and it plunges into the primary. The primary, however, is almost unaffected by the tidal interaction. So therefore, if a hotspot forms where the secondary material plunges into the primary and sets off a detonation, it will actually run a detonation through the primary, which is an almost undistorted subchandrasekhar mass white dwarf. So therefore, this actually falls into the category of subchandrasekhar mass white dwarf explosions, although it's a merger that in total has a mass that is above the Chandrasekhar mass. Now, this was originally tested for two low mass white dwarfs with a mass ratio of 1:1, giving rise to a rather faint event, but later on, Rüdiger-Packmore tested this also for other scenarios. So this setup here with two unequal mass white dwarfs, more massive white dwarfs, actually produces 0.6 solar masses of nickel-56. So this would be a good candidate for explaining normal type 1a supernovae. The big question in this scenario is, of course, whether or not in this violent merger scenario you achieve conditions to trigger the detonation in the in-spiral and merger phase. And so originally we argued that this was actually just achieved by heating up the material where the secondary plunges into primary. It's not clear whether this is a robust mechanism, so it's hard to resolve this in SPH simulations. But recently, Rüdiger actually performed such simulations of violent mergers of two white dwarfs with a new numerical technique. He used the cosmology code Arapo by Volker Springer to follow the in-spiral and the merger. The Arapo code is a grid code that, however, employs a moving mesh so that one can follow such Lagrangian problems very well and with very high accuracy. The advantage of using such a grid code that in addition has adaptive mesh refinement built in is that it allows for resolving very, very small mass transfers between these two stars before the actual merger takes place. So Rüdiger actually placed the thin helium shell on top of the carbon-oxygen subchandrasekhar mass white dwarfs that you would expect to be there from stellar evolution. So they have masses on the order of 10 to the -3 or so solar masses. And with the Arapo code, it's possible to really resolve these very thin helium shells. And then what happens actually very close to the merger, so the merger has not really happened yet, but it's very close to merge the system, that then it will actually start to transfer this helium first in an accretion stream that you can resolve in the Arapo simulations. And this is an unstable accretion that leads to hotspots forming on the surface of the primary white dwarf. And helium is easy to detonate, and in this way you find a way of igniting a detonation in this scenario. Of course, what you detonate here is a helium shell, again a thin helium shell, but we have shown already before that if you ignite a helium shell on top of a substandard Saker mass white dwarf, it will drive a shockwave into the center and triggering a secondary detonation in the center of such a configuration because of this spherical shock convergence and amplification is easy. So this seems to be a promising scenario. It avoids the disadvantages of detonating a very massive shell and leaving behind heavy species that could obscure the predicted observables. And it takes, however, advantage of the good performance of subchanneler Saker mass detonations, pure subchanneler Saker mass detonations. The question is, of course, whether the detonation ignition is a robust process. Now, for the subchanneler Saker mass explosion scenarios, not only the merger model, but in general, there is a fundamental problem. And this is that you know roughly what the brightness distribution of normal type 1a supernovae is. So a typical type 1a supernova should produce 0.5 solar masses of nickel 56. And for doing that, a 1 solar mass carbon oxygen white dwarf star is needed. If you detonate a 1 solar mass carbon oxygen white dwarf, you will produce on the order of 0.5 solar masses of nickel 56. But the range where you can do this is very narrow. So if you actually go to 1.1 solar masses, you will produce already much more nickel 56. So then the question is, why are these CO white dwarfs with exactly 1 solar mass favored? So this is not clear, and this is something that the models still have to answer in order to be a viable model for explaining normal type 1a supernovae. The only case where this has been studied was the violent merger model. So this was studied with binary population synthesis calculations by Ashley Reuter. So the citation is missing here, sorry for that. And she found that actually by some particular episodes of mass transfer, it seems to be that the masses of carbon oxygen white dwarfs that produce a peak in the luminosity that corresponds to 0.5 solar masses of nickel 56 are actually achieved. Okay, so last slide, the other scenarios. Actually, there have been other scenarios for thermonuclear explosions of white dwarfs suggested, but actually for not many of them, actual numerical simulations of the explosion phase have been presented. An exception is the collision between two white dwarfs. So white dwarf collisions have been simulated by two groups, by Stefan Roswog and collaborators and by Cody Ruskin and collaborators. They actually looked into slightly different setups. So Stefan Roswog looked into straight head-on collisions only with rather massive white dwarfs, and Cody Ruskin actually looked into grazing collisions as well with certain impact parameters. What both groups found is that a detonation is likely to form in the collision region. However, it propagates asymmetrically, and if you have a head-on collision of sufficiently massive white dwarfs, say on the order of 0.9 solar masses or so, then you will also be able to produce a substantial amount of nickel 56. So this is shown here from the simulation by Stefan Roswog. We have the head-on collision of two white dwarfs in this direction here. And this is the carbon, nickel, oxygen, and silicon produced in the detonation. You see that the nickel 56 that's produced here has a very oblate shape. So this is actually where the collision gives rise to the strong compression of the material. So that's a prediction of these models. You would actually expect to have a very asymmetric structure, chemical structure of the ejecta. And the question is whether this is consistent with polarimetry observations of type 1a supernovae. Okay, so that's all I wanted to say about scenarios of explosions of thermonuclear explosions of white dwarfs in different simulations. So tomorrow we will then summarize the observables that have been derived from such explosion scenarios. Thank you very much for your attention.
Just a very quick word before we get questions from it. Since we are not sure the sun will be shining so brightly tomorrow, we will do the group picture now, just after the questions. So here I have a very nice place, quite clear for the hotel. So right after the question, we will hurriedly there, and only after that we will let you get your coffee and croissant. So do you have questions, please? Yes, in the beginning. She was the ladies, okay, so then
I didn't catch exactly from which parameter is modeling depends the moment when detonation replaces deflagration.
Well, the parameters, yeah, I mean, the parameters are not clear. So the thing is, the picture that one has, but this is not a proven model, but this is just a picture, is that you think that in order to get a detonation running, you would need to precondition the material so that the Zeldovich gradient mechanism would work. You would need a very, very shallow temperature gradient. So the idea is that at some point, the deflagration flames will become very broad. Turbulence will actually interact with the flame, and in the preheat zone, it will actually lead to conditions that are sufficiently shallow in the temperature gradient so that perhaps a detonation transition can happen. So that means the parameters from that picture, it's not a model, it's not proven that it actually works, but if it was to work, you would actually expect that this happens at low fuel densities, because only then the flame is broad enough that you have interaction of the flame structure with turbulence, and you need still strong enough turbulence. And these are two counteracting effects, because in late stages, when the densities are low, the fuel densities in the flame has become broad, then turbulence also starts to freeze out already. So you want to have broad flames, but still sufficient turbulence. And this is actually what you want to achieve, and this is what we're looking for. And this is how we parameterize, in the end, the deflagration detonation transitions with our subgrid scale model in our simulations. Other people just assume a free density parameter and say, well, once the flame reaches 10 to the 7 grams per cubic centimeters, a detonation triggers by some unknown mechanism.
And also considering the plot, when in this delayed detonation scenario you received the different mass of negative 56.
The delayed detonation, yeah, okay.
Yeah, from what it depends also.
Well, in this, so the plot that I showed was actually from the sequence of models that we performed where we varied the deflagration ignition density.
No, with this delayed detonation, we show that you can receive big range of
yes, right, this here, right?
Yeah. So what you changed?
We changed the ignition of the deflagration. So this is an effect that I tried to explain before in these plots here. Basically, that if you have a strong deflagration ignited by many sparks, then the star will expand a lot, and when the detonation triggers, it will see only low density material and doesn't produce a lot of nickel 56. If you actually have a sparse ignition, then the deflagration will be weak, the star will not expand a lot, and therefore the detonation will burn a lot of material to nickel 56, and that makes bright events. And this is actually a parameter that sets, in the end, the overall brightness. But it relies on the fact that you can have a large variation of the strength of the deflagration by changing the number of ignition sparks. And it's not clear, so this is not really supported from pre-ignition convection simulations. So they would actually indicate more that you have a one bubble off-center ignition. So this would be this case here. And if this was really true, then the outcome would be in delayed detonations only very, very bright events.
Somewhat related to this, how is the whole business starting? You mentioned yesterday a lot of numerical constraints, and I'm not sure what the conclusion is. Is there a chance to get to this initial ignition self-consistently, or do you always have to start with some parameterized?
Yeah, I think this was the idea that Mike Zingali and Stan Woosley had, that they actually wanted to do these pre-ignition convection studies with the Maestro code, the low Mach number anelastic code. And then this code was actually developed together with a compressible hydrocode, the Castro code, with the same grid geometries and the same input physics, so that the idea was that once you have actually seen a hotspot and think that this is where the flame may ignite, you can map over to the compressible code and do the supernova simulation. Well, this has not happened yet, but I think this is something that people can do at some point. But this actually will...
There's also this question about real numbers.
Yeah, I mean, this of course, I mean, you don't know whether you actually solve the real physical problem. This is one point, and you will not be able to really self-consistently resolve the flame formation. You see the hotspot in these pre-ignition convections, but whether or not you really form a flame, this actually still has to be set in by hand at this point. But at least, I mean, what you can achieve is actually that you set off the ignition and a background state which actually was prepared by these convective motions. So you have the convective flow velocities and the convective flow field already in. The expectation, however, is that the convective flow velocities due to carbon convective burning are rather low compared to the flame propagation speed, so it will not have much of an effect.
Ich glaube, das